Let me say thank you to Christian and the rest of the organizers of this meeting, and congratulations on having a new center. It's nice to feel like a neighbor of this activity, and also one where we're involved in a similar kind of cross-disciplinary or multidisciplinary activity where quantum is a unifying theme, but a lot of other activities that each have quantum as part of their theme are brought in. After all, the world is described by quantum mechanics, so there's very little that wouldn't fit within something called a quantum center. This is a talk of research that's been done recently spanning materials science, condensed matter physics, and ideas in quantum information, much like the kind of breadth of the theme of this new center here. And I would like to particularly highlight that in my view, the breakthroughs, if any, that I'll be talking about are principally materials science breakthroughs, something which often gets, particularly by condensed matter experimentalists, kind of swept under the rug, like we get our materials from the FedEx truck if we're involved in collaborations. But here I want to flag it as something absolutely front and center to the collaboration. This is a talk about topology and its relationship to information storage, retrieval, and processing. And it's not a new idea, at least in classical physics. It's been understood that information can be stored in knots for a long time, and that it's actually, given the 5,000-year-old records that are still traceable, findable, and decodable of how information was stored and recorded in Mesoamerica, a knot is a very effective way to hold information for a long time for the same reason that we're going to be talking about here, which is that it's immune to a lot of environmental disturbance. That is, you can do a lot to a piece of paper or to anything that contains information and wipe out that information, but it takes a concerted effort to untie a knot. It takes a very special action of the environment to remove a knot from a piece of string. And it's a fair question to ask whether or not there's a similar concept in quantum mechanics, that the fragility of a quantum state to being measured and therefore no longer having the superposition principles of quantum mechanics can be made more robust by encoding the information in some topological structure. That is maybe a shorthand version of asking the question, can you tie a wave function in a knot? And if you can tie a wave function in a knot, can you make it so that decohering that quantum state by a, let's say, non-intelligent environment, an environment which acts locally in a random way, will not be able to effectively untie the knot and remove the quantum information? It's an intriguing idea given what we know about classical physics, and it seems, at least theoretically, that the answer is yes, it is possible. It hasn't proceeded very far, like much of quantum information, hasn't proceeded very far down the path of realization. But this one, and I have to emphasize, is particularly in its infancy. But the fascinating concept of encoding information in a way, topologically, that is immune from a decohering environment is a very attractive idea, and one that it seems to me to be worth a considerable experimental effort. How do you do it? Well, it takes advantage of some aspects of quantum mechanics which are not, let's say, not in chapter 1 of a quantum mechanics textbook, but maybe in chapter 3 or chapter 4. That is the particle statistics. So particle statistics, as you recall, has to do with whether or not upon, this is a particularly dim light bulb, maybe. Well, it's not so bad. Can you all see that red tip? Is that okay? Not so bad. Okay. Particle statistics concerns whether or not when you exchange the position of two identical particles, whether the overall two-particle wave function picks up a minus sign. And we know that in 3 dimensions that there are 2 kinds of particles, bosons, which don't pick up a minus sign when the particles are exchanged, and fermions that do pick up a minus sign. Let's see if that one does anything different. Thanks, Yuka. Oh, boy. And they both have the property that a double exchange, which is equivalent to one particle surrounding the other, restores the wave function to its original wave function. The two-particle wave function, upon moving a particle around another particle, recovers the same wave function. That is, there's no memory that that action occurred. And that's a useful thing because in 3 dimensions, or you could say that the world should be constructed that way, because in 3 dimensions, there really isn't much meaning to the idea of surrounding something by something else. You can see immediately that that doesn't mean anything in 3 dimensions. Just like I could say, for instance, that I'm surrounding your head with my finger. To me, I'm surrounding your head with my finger. And then if I went to someone in the very back row, I would be doing it like that. So it doesn't mean anything. That is, it can be contracted to a single point in 3 dimensions. And so there shouldn't be any memory of my having gone like this with my finger affecting his head. But in 2 dimensions, there is the notion of something surrounding something else. And there is an unambiguous trace left. If you imagine, for instance, a string hanging down in some 3rd dimension, there is an unambiguous notion that this guy went around the other one because it would be left behind as the memory in these strings of who got wrapped around who. In fact, you could even say that everything like weaving and carpet making and crocheting is encoding the memory of which ends of the string went around which to produce cloth or carpet or any other pattern. So that in 2 dimensions, these memories are preserved. And so we might begin to think about whether or not we can encode information topologically in the form of who went around who without any direct interaction by looking in reduced dimension. So I looked this up just as a joke. You can, on the internet, you can buy anything on the internet, including magic wands that are not so cheap, but there's many different kinds available. And the question is, this idea of surrounding something without anything emanating from it, but just changing the state of something, like turning a frog into a prince or a prince into a frog by moving something around it with a magic wand, is something that we can now say probably can't work in 3 dimensions. But it may, in fact, work in reduced dimension. It is conceivable that you could move something around something else and change the state of the thing that you've moved around, because the world will know that that has surrounded it once. And now we just have to find quantum mechanical systems that behave like magic wands. And we don't have any yet, but the theorists haven't slowed down in telling us what we would do with them if we did have such particles. And I won't, go into the description of this. Suffice it to say that if we had particles that could encode information, all kinds of quantum mechanical operations that would form the elementary operations of a quantum computer have been worked out. So we're not going to run out of things to do once we figure out how to move something around something, and by braiding the particles in time contain information, we'll be able to make gates that can perform quantum mechanical operations. And you say, well, big deal, there's lots of other versions of these kinds of gates that exist in other kinds of quantum bits. The notion would be that this particular formulation has an extremely long coherence time, simply because to decohere a state that has been wrapped around something else, you would need to somehow act non-locally in some intelligent way to remove the braiding operation. I should say that one of the very positive aspects for my research, and now coming to Finland also, is that the Microsoft Corporation got interested in this problem, courtesy of a mathematician, this guy on the left of this picture, who's a topologist, and who became fascinated with this problem and convinced the management of Microsoft that this was a worthwhile thing to invest in. And they're sponsoring this research at a very fundamental level. And it's I think that, at a kind of at a higher level, it's very interesting to see corporations becoming interested in quantum information in a way, if a corporation is interested in something, the way you can tell is that they'll spend money on it. And to see not only Microsoft, but IBM and Google and other companies beginning to invest in this technology, and you can ask the question, why? What are they going to get out of it? Do they believe that this is just for fun? And I would say no, companies don't generally do things just for fun. So these are technologies that may, in fact, someday be replacement technologies for conventional computation on particular problems that are either intractable or don't scale well, meaning that as the problem becomes harder and harder, the classical approach to those computation problems becomes sufficiently difficult that, that it pays to, for instance, cool manufacture and under somewhat difficult circumstances, not use silicon, etc. It may pay to take that disadvantage given the proper scaling of these quantum algorithms. So it has been identified at a core physics level what kind of systems you could build that might produce these kind of particles that can be wrapped around each other and will remember that they've done it. They don't seem to exist in nature anywhere. We don't seem to find naturally occurring non-abelian, as they're called, or topologically non-trivial particles. And so you might think that anything that doesn't occur in nature simply doesn't exist. But then, of course, we have lots of things that don't exist in nature, like high-temperature superconductors. Probably without an intelligent mind assembling those ingredients, they wouldn't have assembled themselves anywhere in the universe. So without an intelligent actor in the problem, perhaps high-temperature superconductors simply wouldn't exist. And it may be the same thing with these non-abelian particles. Without an intelligent actor assembling the ingredients to produce the necessary requirements, they may not exist in nature. They may not exist anywhere else in the universe until you get to the next planet with intelligent life on it that put the ingredients together. But that doesn't mean that it's not a fundamentally important particle. It just means our minds were part of the natural process that produced them, which is an interesting thing to think about. So if we say that there aren't naturally occurring non-abelian particles that can remember that they've been braided around each other, how would we assemble them ourselves? Well, an important theoretical discovery, I would say, was made, tracing itself probably back to Alexei Kitaev and maybe others, who recognized that a superconductor that has a spinless character, that is, when the two particles that need to pair, which are normally paired in a spinless configuration, so-called S-wave configuration, one up, one down, or a singlet configuration of the two electrons that pair in a superconductor. When there aren't two different species that can pair, then the system has to pair with a unit of angular momentum to preserve the overall anti-symmetry of the electrons that pair in the wave function. If that happens, then in reduced dimension, that special kind of one-dimensional so-called P-wave or spinless superconductor has at its ends excitations. And those excitations have their own particle statistics. They're created within the superconductor and live at the boundary of this superconducting state. So I wrote up here, at the boundary of a spinless one-dimensional superconductor, there will exist excitations, and theory tells us, with only scant experimental evidence, and I'll show you that evidence today, that the excitations that exist, the red balls that I've drawn at the end of this picture, not I, actually, Jason Alisea drew at the end of the picture, have non-abelian statistics that can braid and remember that they've gone around each other. So this would be the first experimental evidence of such a particle anywhere in nature. And isn't it interesting that it just happens to live in a regime which is a little bit hard to get to? You need a dilution refrigerator. You need superconductivity. You need a one-dimensional crystal that has strong spin-orbit coupling. And the material has to also be susceptible to an external magnetic field that must be sufficiently weak that it doesn't destroy superconductivity in the superconductor that seeds the state, but it has to be sufficiently strong that it can produce a Zeeman splitting, or a splitting of spin up and spin down in the superconductor, which exceeds the gap of the superconductor. And it looks like here in the 21st century we have all those tools in hand, and that it's possible to assemble such a system now. So here are the ingredients: a one-dimensional crystal that has strong spin-orbit coupling and strong Zeeman interaction in the form of the G factor. That produces a band which is the shape of this W at the bottom that is spinless, and in the presence of an external magnetic field, here represented by the letter H, which exceeds the superconducting gap induced in the material. When H over delta, the gap, is larger than 1, a new type of superconductor exists, a superconductor whose excitations at the end have non-abelian braid statistics. That's what theory tells us. Theory goes on to say that if you could move those around each other in some way, like for instance to wrap number 1 around number 2 by moving number 1 down here, then moving number 2 over, then moving number 3 back up, just like if you have to pass someone in the aisle of an airplane, someone has to step into the aisle, and then the other guy can go back, then you can step back in, and then you can pass each other even though it's in one dimension. In that kind of braiding operation, you can wrap objects around each other, and if so, you should be able to detect that you've done so, and you should be able to see that you can encode information by the time histories of these red balls moving around. Now, in practice, because these are semiconductors, you don't have to actually move the red balls, but rather you can put gate voltages on and deplete the semiconductor, which moves the end state of the semiconductor to being the location of the undepleted region of this proximatized semiconductor. So you can make all the red balls that you want by just depleting intelligently where you want to have conductor and where you don't want to have conductor. That's one of the nice things about inducing superconductivity, not in a metal, but in a semiconductor. Because in a semiconductor, you can deplete the carriers, and you can then position the red balls where you want using electrostatics. Now, I've gone on for a little while without anybody asking a question. Is that because it's clear? Yes. Thank you.
You said that there are excitations, so basically at 0 temperature, or at so this, you said that there are excitations, so at low temperature, would it just be without these excitations? You have to somehow excite the superconductor or the wire?
No, they exist by necessity at the boundary of the end, and that is they're a zero energy state. So I would say maybe excitation isn't the right word. They are the edge. They're the edge of this conductor, and that they live at zero energy at the boundary. Much like in the quantum Hall effect, there's an edge state which can carry electricity that lives at the edge of this otherwise gapped system only at the boundary. This is the boundary of a one-dimensional system, and there at the boundary live these states. And so they are part of the ground state of the system. Yeah, I shouldn't call them excitations. I should call them emergent states, just as the edge state of the fractional quantum Hall effect is an emergent state at the edge.
Okay,
Yeah.
Thank you. Then I have another question about
Sure.
the braiding. I can see that you can move like this with the gate voltages. You can swap 2 particles or move them around. But if you have more, like if you have 4 particles, and you would try to if you have 2 pairs, and you would like to go around with 1 particle in 1 pair around another particle in another pair, wouldn't you somehow need to then destroy that second pair when you deplete that gas?
Well, what exactly happens at the intersection is a complicated story, and because the answer is yes. Theory tells us exactly what precise gate voltages to apply in order to affect a braid. So the literature is there. Now, whether we experimentalists can do what they say to do is a different question. But in terms of the conceptual possibility, yes, it has been as well. Now, look, you could challenge me just as effectively on saying, what exactly is going on at that intersection right there? What is that? And is there an extra red ball at that intersection or not? You say, yeah, that's right. This guy just drew it in PowerPoint. Now we have to go make it in the lab. So that's an important point. But at a conceptual level, you can see that if you could make this thing all topological, you could do this operation. That's not that hard. And so at that same conceptual level, you can braid successfully. It remains even to do this for the experimentalists, though. Okay. Any other questions? Yeah?
So do the edge states have to...
Oh, you're supposed to talk into the box.
Yeah. So do the edge states have to break the symmetry in such a way that you have not necessarily exactly S wave, but perhaps a D or something like that? How they can be protected if they can keep the symmetry the same? I mean...
Yeah, so by the way, that's right. They're not S or... Because of the presence of spin-orbit coupling, you see there's a kind of schematic representation. That blue arrow is not parallel or anti-parallel to that red arrow. And that's supposed to be a graphical indication that these are neither fully S nor fully P, in the sense that this state is, partially spin up. It's spin down when it's moving to the right, and it's spin up when it's moving to the left. But it has enough S character that it can proximatize. But it's not fully S wave either. That's I think the point to make, which is that it has a P character, which means it has this non-abelian character, but it has to be able to couple to an S wave superconductor. So it can't be either. Otherwise, it would be very simple to make a spinless, you just put it in a Zeeman field. And one guy would go up and one guy would go down, and you'd have the guy that went down, and you'd say, well, there's a spinless state. The problem is that it's spin-aligned, so it can't proximatize. This has to rely on the spin-orbit coupling to allow it to proximatize. Now, you asked, okay, so I think that was part of the question, but there was maybe more to the question than that.
No, that's...
Was that it? Okay. Okay, let me press on. I'm sure there'll be more questions later. But you see the goal now. The goal is that theoretical physicists have said that there are red balls at the end of one-dimensional superconductors. Okay? And they may be right and they may be wrong. If they're right and those red balls have this property, we have to figure out how to detect it experimentally. Actually, they gave us a little more of a clue than that. They even told us what materials we should go looking in. What materials might have sufficient spin-orbit coupling and Zeeman splitting. Materials like indium arsenide or indium antimonide, that if you plug in the numbers, you get very optimal. Oh, that's a good point. Would anyone mind if I just took a minute and plugged in my computer? I was going to do that when I got up here and I forgot.
On the desk.
Is there a place to do that? Great, excellent. That saves all a lot of... Okay, that should be happy now. Okay, so we were given a lot of information by these analyses of whether or not the parameters of these particular materials were sufficient to reach the regimes that were predicted. And we wouldn't have even started down this experimental road had we not had enough calculations and enough experimental information about the effective mass, the spin-orbit coupling, the G factor of these semiconductor nanowires that produce these one-dimensional materials. So I'm going to be talking about experiments in indium arsenide. Some other experiments have been done in indium antimonide. But these are the materials that, because they're small band gap semiconductors, they have strong spin-orbit coupling and greatly enhanced G factor. And those are the two criteria that we need. And of course, they have to be able to be proximatized by coupling to a conventional metallic superconductor. But if we can do it, the numbers look good. Now, in fact, the theorists didn't stop there, because we experimentalists weren't going very fast. So they had a lot of free time on their hands. And so while, after telling us exactly what to do in the laboratory, they went on to tell us, once we got that working, once we can make the little T junction, they're not red here, they're yellow, but it's a different theorist. Exactly what we should do in order to turn the whole thing into a topological quantum computer. So it's fair to say that it's not like we don't know what to do with these things once we have them working. We've sort of had our next 10-year work plan laid out for us, whether or not we want to use fluxes or voltages or quantum dots to affect the operations we know what to do, and different experimentalists in the field prefer different versions of this and are trying them in a kind of a competitive, collaborative way to see which one works better. But first, don't you think that it would be wise to find out whether or not there are any red balls there at all? Before we start building quantum computers out of them, we should see whether there are such things. And so we have been instructed that the presence of a Majorana fermion, as these things are called, or a Majorana end state, gives a very particular signature that the topological superconductor that supports those Majorana states at their ends, here X is a spatial dimension, so this is one end and this is the other end of a finite superconductor, measuring the density of states, and you can see, if you're familiar with superconductors, a traditional so-called BCS or a superconducting density of states, and nothing below the gap. This whole area in energy below the superconducting gap has no density of states at all, like a regular superconductor, except, unlike a regular superconductor, it does have a strong density of states at its ends. That is, at zero energy, you can tunnel a state in. You can tunnel an electron in or tunnel an electron out. You can't do that in a normal superconductor, and so that's a distinguishing characteristic of these red balls at the end of the wire. That is, you can tunnel an electron into a red ball. It provides a density of states for regular electrons to tunnel in. You can run current through a superconductor, but only in electron pairs. You can't tunnel a single electron into a superconductor. So you can imagine, as you turn up the magnetic field and go from the regime which is topologically trivial, the regime in which there's a BCS density of states, and now they're calculating conductance from a tunneling experiment into a superconductor. Here's the BCS density of states for a realistic sample with disorder. As you turn up the magnetic field, those two states move toward each other, and instead of continuing to pass through each other as their Zeeman split, instead they form a new state, a state that lives only at zero energy and persists up to higher magnetic fields, and is the signature of the appearance of the red ball, or the topological state at the end of the wire, which would only appear as the magnetic field is raised above a certain critical value. So it's a pretty well-defined experimental signature, and it didn't take long after those papers for this beautiful experiment from Delft, from Leo Couwenhoven's group, to appear, in which a superconductor, in this case the superconductor was niobium tinitride, was applied to an indium antimonide nanowire, making contact on one side. These gates that run underneath the wire could produce, right where my green spot is right now, the tunnel barrier, so that you could tunnel into the end of the wire and find out whether or not the tunneling into the end of the wire was allowed at zero energy, indicating the presence of a red ball at the end of this superconducting wire, this proximatized wire. And then the tunneling experiment would go into the normal end that you could just tunnel out. That would be a way to provide the normal electrons for the tunneling. And by making these barriers rather opaque, you could find out whether or not you could tunnel a normal electron directly into the superconductor at zero energy. And the experiment indicated that at zero magnetic field, sorry, I chopped off the magnetic field here. This is a magnetic field in Tesla along the horizontal axis. At zero magnetic field, no, you cannot. There was a dark spot in the tunneling density of states indicating that there was no electrons states available for tunneling. Here you can see in the zero magnetic field data, below this BCS density of states, this big valley indicating that it's difficult to tunnel in. As you turn up the magnetic field to a value which is roughly the Zeeman splitting in indium antimonide equaling the gap, a peak would appear, and the peak would appear at this value of magnetic field. And you would have liked, of course, for the peak to have persisted up to higher magnetic field, and God knows what all of this stuff is, but in any case, a peak appeared right at the right value. And like a typical experiment, it didn't look like a plot of theory, but it looked like it had a lot of the key signatures. And the paper went on to study the orientations in magnetic field and really rule out a lot of alternatives, and came out with a very bold claim, which was these so-called elusive Majoranas are evidently not that elusive at all. The first time you put the materials together that wouldn't have occurred naturally. They really wouldn't have even occurred naturally in anybody's laboratory until instructions were given to put them together. And then once the instructions were given to put them together, well, lo and behold, there it was. Within a year or so, other labs around the world were seeing the same thing. That is, here's from the Weitzman group, Modi Heiblum's group, a slightly more complicated density of states, probably one so-called Andreev state below the gap. Here's this edge of the BCS density of states. Turn up the magnetic field, and that dip becomes a peak and then goes away again. The same kind of thing, a very characteristic peak. It's true that you would have liked it to have done a little more of what the theory indicated that it should do, but it was at least surprising that this density of states should appear right out of nowhere. And in fact, what was turning out from the elusive Majorana to be more like the ubiquitous Majorana, everybody's experiment all gave the same data. All of us led by Delft to say, put these ingredients together and you're going to find it sitting right there, right where you think it should be. This was from our own lab at Harvard. This was one of the last experiments that I did there, already in collaboration with the Lund group, Hanki Su and Mintang Deng from Lund, and Kasper Grove Rasmussen from Copenhagen already at the time. But as you turn up the magnetic field, this is not a particularly good density of states, nor is this a very deep tunneling regime. In fact, it's a highly conductive regime. But boy, you just can't help but turn up the magnetic field, and all of a sudden, boom, this density of states would produce a peak, and you just couldn't get away from it. So if anybody has any doubts about the Delft experiment being reproducible, let me tell you right now, it's hard to not reproduce it. And that's very interesting, because, you know, the question of the elusiveness of these particles is I think, shrouded in mythology. They're not elusive at all. Now, that doesn't necessarily mean that these are Majorana red balls. It just means that they're passing all the tests of the Majorana red balls. Of course, it could be something else that happens to have all of those same characteristics. Here's an example of something in which you can see, it's a little bit hard to see on these data. Here's something that looks like a BCS density of states ridge. This is in an indium arsenide nanowire, the same material. Now there's two superconductors on the two sides. You turn up the magnetic field and bango, this gigantic zero bias peak shows up. And I can tell you that this zero bias peak has nothing to do with the presence of a Majorana state at the end, because it persists long after the destruction of superconductivity. This peak is the Kondo effect. And it appears at finite magnetic field because you have to destroy the superconducting state before there's enough normal carriers in the leads to have a Kondo effect with a bound spin on the dot. So there is physics that will produce a finite field onset of a zero bias peak. It's not sufficient to say that's the Majorana. And like the other experiments have done, you have to look at field angle, you have to look at different materials, etc. So it's passing the test, but not because there aren't things out there that are disguising themselves as Majoranas. And so, you know, care, like with any experiment, has to be taken. I want to, for the moment, turn my attention to another problem, which was, this was supposed to be a tunneling measurement of a BCS density of states below the gap. And what you saw over and over again was like this numerical experiment of something that below the gap looked like this sort of soft valley below the gap, and not really anything that you would call a self-respecting density of states of a superconductor. And you can ask, you know, how did that happen, and what does that tell us about the experiment? I should add that for the point of application to topological information processing, this sub-gap situation is a disaster, because even one free electron below the gap will participate in braiding. And you have to do the kind of thing which is a real specialty here in Finland, which is you have to make a superconductor that's macroscopic in size, in which every single one of the electrons is removed from that superconducting state. Any one electron that's in there will participate in braiding, will alter the states that have been moved around it, and will kill the topological protection. So this thing is not only a mystery and a kind of an annoyance, but it's death to topological quantum information. If you read this theoretical paper, I'll just give you this line from the abstract. It says, we find that interface inhomogeneity, the interface between the superconductor that has been put on to proximatize the wire, we find that interface inhomogeneity with moderate dissipation is the only viable mechanism that is consistent with the experimental observations. Okay, well, that's a pretty strong statement, but in any case, you get the point that interface inhomogeneity is responsible for this, in the numerical experiment, for this soft gap, as they call it in the title. The work indicates that improving the quality of the superconductor-semiconductor interface should result in a harder induced gap. And that brings me to the material science part of this talk, which has to do with the developments from the materials group in Copenhagen, led by Jesper Nygaard, and particularly pushed forward by a remarkable postdoc named Peter Krogstrup, that when these nanowires are grown from catalyst gold particles on an indium arsenide substrate, these are indium arsenide nanowires, and then by adjusting the temperature and the pressure in the growth chamber during the MBE growth of the nanowires, aluminum can be deposited on the side of the wires. There's already aluminum in this growth chamber because it's a so-called 3-5 growth chamber, so aluminum is already in the MBE system. You can produce an interface between the aluminum and the indium arsenide that is epitaxial. That is, it will grow with atomic registry between the aluminum, which is not lattice matched to the indium arsenide, but it will find an angle to lattice match to it. And I should say, this is, I would say, a remarkable discovery. This is the current issue of Nature Materials, and there's a picture of that interface. And you can see from this picture what a remarkable interface it is. Here's the indium arsenide with its complex crystal structure. This is a transmission electron micrograph, and aluminum on the other side. And it just finds the angle that produces the epitaxial match to save energy, and it has to be done at just the right temperature. But now that there's material that has as intimate a connection between a superconductor and a semiconductor as you can possibly have, you can now revisit some of the geometries that we saw before. The story is even more remarkable than that, because if you look at how these nanowires are grown, Peter has figured out a way in growing these materials that the catalyst particle that is responsible for this upward growth of these can be, by changing the temperature, induced to move around the side onto one of the facets of the nanowire, this hexagonal cross-section nanowire, and then grow out in a transverse direction in a different crystal orientation, moving sideways, and that sideways growth also is epitaxial on its interfaces when aluminum is added to it. So you have two different materials, in effect, with two different amounts of spin-orbit coupling and two different G-factors that both have this epitaxial property. To make matters even more remarkable, if you put the catalyst gold particles in a hexagonal orientation on the substrate, that is, you just deposit, using electron beam lithography, the spots where you want the wires to grow in a hexagonal pattern that's registered with the hexagonal orientation of the crystal itself. Then, when the wires start growing out of the side of one of those facets, they'll aim themselves directly at one of the other wires that's growing up from the side. And in doing so, they'll begin to produce a network of wires that grow in this kind of orientation, so that you could even have complicated and, in particular, T-shaped structures, which are the key to these braiding operations and looped structures, etc. So this is far from a perfect crystal, but it's enough to do demonstrations of braiding because we have this epitaxial growth from this aiming of the lateral wire. It's pretty remarkable. I would think that if you didn't know me and I was just telling you this, like, at a bar or something, you can grow them, you go sideways and it hits the other guy and then they grow epitaxial, you would just think I was crazy. But when you do it, here's a case where the MBE system was rotated during the growth of the aluminum, so the aluminum goes all the way around it, but you'll see that that doesn't matter as we continue. If you make a tunnel barrier just like in the Delft geometry and you make a tunneling from this proximatized superconducting state into a gold lead, you'll find now the hard gap is restored, and as a function of magnetic field and temperature, the curves reproduce exactly what you would expect theoretically. Here is the theoretical curve for what happens as a function of magnetic field. Here's the theoretical curve for what would happen as a function of temperature, and you see that you're just getting exactly what you'd think you would get. So that theory paper about the soft gap appears to be correct. The quality of the interface seemed to make a lot of difference. You're making a face like you're confused, so probably a lot of other people are confused too. No? Is that true? No, you with the red hair. The box. Okay. Was that
okay?
Oh,
I was just wondering about the graph in the top left. It looks like as if actually both of your leads of a tunneling junction would be superconducting.
Sorry, say it one more time.
The curve looks like as if both of your leads of your tunneling junction would be superconducting, and not just one.
Both of the leads. No, I don't think so. This is a measurement of the conductance.
Yes.
And it's a tunneling measurement into a superconductor. So it should look like one BCS density of states. If they were both, then it would look like two densities of states.
No, not if they would have the both gap, the same gap. I'm just wondering because the resolution is quite. Anyway, it's not so important. I mean, I didn't want to ask.
It's true. You weren't going to ask. That was my fault. That was my fault.
You wanted a question.
I'm not going to fault you for that question because I was the one who induced it. But in any case, this is, I think, because you're probably an expert, just like a BTK, Blonder-Tinkham-Klapvik tunneling into a superconductor from a normal lead. So this continuum, barrier, BCS, tunneling measurement as a function of source drain should give, at low conductance, a BCS density of states, and I think that that's what that is. Let me press on.
Another question.
Yeah.
Back to the density of states.
Yeah.
So you have sharp gap, but you have some remnant conduction in the gap at zero field.
At zero field, you mean down here?
Yeah. So what is
Well, no, the zero is off the axis. It's pretty close. It's about a factor of 100
okay.
below.
Okay.
Yeah.
Just comparing the other one. Okay.
Yeah, it's better. Yeah, well, that just because that one was plotted with the tick mark, not on the zero. That's.
Sorry.
Yeah. It's 2 orders of magnitude. It's better to look on a log scale. If I showed you this thing on a log scale, which we have pictures of, you'll see that it's about 100 times below the above gap conductance, and 100 actually isn't enough. It's going to have to get better than that even, but that's as good as we've gotten so far. So why? What's the remaining? Why doesn't it go down super low? Well, first of all, we run out of temperature. So temperature starts to play a role. 30 millikelvin or something like that? You mean you say it should be low enough? Yeah. Okay, then we don't know. It still seems to have some temperature dependence, so maybe it's not equilibrated. That's maybe worth thinking about. But in any case, well, actually, you can see. So here's 19. This is mixing chamber temperature, so it doesn't really count. Yeah, you can see it would be easier to see on a log scale. At the edges, it starts to come up a little bit, but in the middle, maybe it's all the way down already. So we don't know why it's only a factor of 100 and how we get it better than that. I don't know, you have any thoughts on how to get it better than that? Yeah. So, okay. Let me show you some interesting devices then made out of these wires, which are different than the ones where it was evaporated onto the substrate. I see I've got about 10 minutes left. This wire changes thickness because it was one of these laterally grown ones. It's one of the sideways geometries. I'm calling this Delft geometry because it really is, in the end of the day, just a superconductor that goes all the way up to a tunnel barrier. Now these are laterally defined tunnel barriers. And I want to try a different kind of experiment where I look at a long wire where there's a Majorana state that lives here and another one that's very far away, and compare it to a short wire where the two Majoranas can feel each other, that they're close enough that they're not at the ends of a long wire. And the theory for that has been worked out, and we can compare it. So I would like to say that if I turn these two side gate voltages, which I'll call PG1 and PG2, this gate and that gate, if I turn those both to 0 so that it doesn't disrupt this wire, I'm going to call that a long wire because there's a Majorana that will live here, another Majorana that will live here at the end of the wire against this normal superconductor interface. But if I deplete number 2, if I deplete the carriers here, then the other Majorana moves up here only a half a micron away from the other Majorana, and the two Majoranas will interact with each other. And now they won't live at 0 energy anymore, and it's a much more distinct signature if they're away from 0. So that's the experiment to see whether that works or not. And you can see what theory tells us will happen when the two Majoranas get close to each other. Here, if the wire is rather long, this was a theoretical study by Stănescu et al., you almost see these two levels, as in the theory that we saw before, come down to form a level at 0 energy, but as the magnetic field goes up, they'll eventually split and start to oscillate. Whereas as the wire gets shorter, the magnitude of the oscillations will be larger, and you'll be able to see that this kind of dance is being performed by the states as they move around. And this is something which is a more distinct signature than just having a bump at 0. It's kind of why I like this better than just looking for a bump at 0, because there's so many different things that can make a bump at 0 that you should make it do a little bit of a dance, and then you can see the characteristics of that dance. So in the case of the long wire, there appears to be a subgap state. We can talk about that later, and as the magnetic field is turned up, the Zeeman splitting of that subgap state appears to go into the continuum. This one appears to come down, and the two of them move together and produce some kind of 0 bias state. Here's a kind of a model of that picture, which is a BCS density of states, two levels that appear below the gap. Those levels are probably associated with some bound state within the system. Those states split when the Zeeman field is applied. One of them goes up, one of them comes down. They meet in the middle and form this, I would say, Majorana state that lives at 0 energy above a high magnetic field. And there it is right there. Now, when I shorten the wire by putting this gate voltage at -3 volts, the character looks different. There's still a subgap state, but now these two levels don't go to the middle and meet. Instead, they appear to cross through each other, go back around, and just coincident with the destruction of superconductivity, they come back around again as if they're going to go for another lap. This one moves up into the into the continuum, while those two move back and forth. The physical picture that I have is that there's these two levels. They split with a Zeeman field. The two of them come back to the middle, but then they're not bound. They cross through each other. They don't stick to B = 0, but instead they cross and eventually will come back around. Now you can say, as a function of that magnetic field, as a function of that gate voltage, when the gate voltage is 0 or positive, it's a long wire. When it becomes negative, it's a short wire. And I can look at 200 millitesla, which is where they cross, and I can see that there's a 0 bias peak until it becomes a short wire, and then they split and begin to oscillate as you move past that point. And you can look at any one of those values, and you can see what, for instance, up here at +2 volts, what the system looks like. It looks like Andreev bound states that split and meet in the middle. As I move down in magnetic field, they stay approximately the same character. As I continue to go down, once they split, I see that now they've taken on this kind of a shape, and they stay that way down for the rest of the journey. So I think that we've begun to now say it's not enough to make a Majorana and see whether it makes a peak at 0, but rather you should make it do something and see if that doing something has the character that the Majorana should have. And so far, so good, although this is early data, and I would say that we would like to repeat these experiments on several devices, make sure that this isn't getting lucky. And you'll know that we in our lab believe that it's real when you see the paper. I think that it's fine to give a talk and to say we see something that looks very tantalizing and introduce a paradigm for how to tell the difference between a Majorana and all the other things that might look like a Majorana. But before you claim that you're now manipulating Majoranas, I personally would like to see it 2 or 3 times, and that we haven't done yet. There's another geometry that I want to talk about in the remaining few minutes, which looks more like a quantum dot. It's one where most of the superconductor has been removed, except for a small patch. You can see here in an electron micrograph, here's the indium arsenide nanowire. It's pretty big. It's about 100 nanometers in diameter. And a very small amount of this epitaxially grown aluminum is left behind, and almost everywhere else it's been removed, and gates are around it to make an isolated superconducting island. It's a different geometry than we saw before, but one that also can shed some light on what are the electronic states that live within the device. When we study this thing as if it was a Coulomb blockaded island, we see interesting conduction patterns, and I'll tell you about those for now. Like with the Coulomb blockade, because electrons can only enter this capacitively this small capacitance island when the electronic state of the next electron is available at the Fermi energy, you see these periodic conduction peaks, which are the familiar Coulomb blockade at 0 bias. But at finite bias, you see something much more interesting in this device, something which I would say has never been seen before. Above the gap, you see something which is periodic and which has a structure of levels that repeats every single Coulomb blockade peak. But below the superconducting gap, there's a twofold periodicity. This guy's pointing to the left, this guy's pointing to the right, this one's pointing to the left, this one's pointing to the right. So below the superconducting gap, there's this flip-flop between the pattern, and above the superconducting gap, it just looks like good old-fashioned Coulomb blockade with subgap energy levels. So somehow below the gap, this thing is able to count whether electron states are even or odd, as if it was true pairing of states. And we've achieved this situation in which there's not a single other free electron in the system. Even though in this piece of metal, there's maybe 10 to the 8 or something electrons, that there are 10 to the 8? No, I think it's, maybe it's 10 to the 8. I have the number written down. Even though there are very many electrons in that piece of aluminum, they're all paired up. And it's keeping perfect track of parity. We can understand this interesting pattern that we see, including these areas of so-called negative differential conductivity, meaning you increase the source-drain bias and the conductance goes down. The current goes down as the conductance has a negative area to it. We can associate that with, again, a situation in which there are 2 Andreev states that live below the superconducting gap, one of them occupied, one of them not occupied. And in the presence of a finite source drain bias, you can identify all these different regions, the X and the square and the circle and the triangle, as being different bias conditions where these Andreev states and the BCS density of states are found, and including this negative differential region. So I think it's sufficient to say that even though this isn't exactly the same as what we see in the experiment, particularly we don't see why this broadens at high bias in the theory, but we understand the general shape. Importantly, at the place where a Coulomb blockade would be if there were a 0 energy state, the location of this X, the value that would produce a Coulomb blockade peak at 0 bias, there is no Coulomb blockade peak. On the next peak, this would be flipped over, and there'd also be nothing there, except all of the structure would be to the right instead of to the left. Each time it flips to the right and to the left, avoiding putting a spot on that value. At 0 bias, this right-left pattern is well studied and well understood. Here's a theoretical paper from 1992 that says in a structure in which there's an isolated superconducting island between 2 normal state leads in the presence of a finite voltage, the Coulomb blockade structure can be understood by representing the energy of a fixed electron number as a function of the gate voltage as being different from even and odd states. When the number of electrons is odd, you have to pay the penalty of putting it in above the gap if it's just a gapped superconductor. And then the next one can go into the continuum because it's a superconductor. It can be part of the superfluid. Then the next one has to go in above the gap, etc. So every one of these associated with an odd number gets pushed up into the air, and that puts this degeneracy point where the two electron states of even and odd are the same at this not evenly spaced pattern. Bum, 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 bum. If this came all the way down, then the crossing points would be evenly spaced, but the non-even spacedness is an indication that the thing has kept track of electron number. The data that I showed you in the previous one with a colored, looks like a footprint going back and forth is just the finite bias version of that same story. Not long after that theory, the experiment was done saying that indeed when there's no superconductivity and all of the parabolas are the same, the Coulomb blockade ladder is equally spaced and was seen in the experiment to be equally spaced. When the system is superconducting, then every odd one goes up into the air and you see little step, big step, little step, big step. And that was exactly what was seen in the experiment. Little step, big step, little step, big step, little step, big step. And that indicated, as this experiment pointed out, that every last electron was being paired in the superconductor. We see a similar thing in the zero bias case, where it's a little bit hard to see from here, but here are the Coulomb blockade peaks, and they indeed go little step, big step, little step, big step, little step, big step. And those little step, big step can be quenched either by turning up the temperature or by turning up the magnetic field. Neither of this temperature are the critical values. That is, it's still superconducting at 350 millitesla, and it's still superconducting at 150 millitesla, but the even-odd structure has gone away. If we analyze the problem, very similar to what was done by Averin and Nazarov, but including a discrete state for this bound Andreev state plus a continuous density of states, we can find the crossing points for the location of the odd versus the even Coulomb blockade peak. And if we do the full thermodynamics of how those states are occupied, I will spare you the analysis here, that you see that the data follows the curve very accurately, and that analysis allows us to calculate the number of free quasiparticles. And by finally finding the relaxation time based on the strength of that negative differential conductivity, we can find the characteristic relaxation time from the BCS density of states down into this into this Andreev state, and call that characteristic time the poisoning time. Now that looks like a lot of analysis, so let me just summarize what the main point of that is. That's a really long time. If you compare that characteristic time to the characteristic time of the loss of coherence of a conventional qubit, 10 milliseconds is a real blessing. That says that you have 10 milliseconds before the very superconductor that's responsible for inducing proximity effect in this system pollutes the state, the Andreev state or the Majorana state, by dropping a quasiparticle, a free remaining quasiparticle, down into that state. You've got about 10 milliseconds on average before that time passes. And that says, we think, plenty of time to do the operations. Let me move on to say, you'll recall that the state was off to the left or off to the right, depending on whether it was an even or odd state. How does that depend on magnetic field? Do we eventually find that it goes back to where it would be if there were a zero energy state? Well, if we draw a line about where it would be when it was a zero energy state, we see that as a function of magnetic field, those two states come together, go apart, come together, go apart, come together, go apart. Just measured from this Coulomb blockade peak position, it doesn't look much like a Majorana, but it wouldn't because it's a pretty small device. By the time we make the device longer, here's one that's twice as long, 400 nanometers, then those states, as you follow them, do pretty much exactly what you might expect those subgap states to do. That is, they're not quite Majorana states because they pass by each other, but they come pretty close and they oscillate just as you would expect them to do. So I think that we're getting to the point after a few more of these experiments, honestly, that it's going to get kind of boring to continue to ask the question, is it a Majorana, is it a Majorana, is it a Majorana, is it a Majorana? It's going to it's passing sufficiently many tests, even now with a kind of a motion as a function of magnetic field, that if there was something else out there that was disguising itself in this many details as a non-abelian excitation, then the only convincing evidence that the particle has non-abelian properties is to braid them and see if you can change the quantum state. That is, it's now time to move on to not looking at the transport spectroscopy, but to actually doing the manipulation, to move them around each other, to see if the quantum state changes. And not just because we're off to build the computer, but because that's the last and most important check of whether or not this thing has non-abelian statistics. I had some conclusions, which I've run out of time, and I will not have time to show. I want to maybe just end with one picture, and that is not data from my lab, but a picture of a commercial product. This is a commercial FPGA chip that you can buy now, and this is a micrograph of the inside of that chip. And this is shocking to me, because these are 20 nanometer lines made with vias, etc. And the reason that I'm showing this at the end is because if you would have just naively guessed what was the hard part of making a quantum computer of any sort, whether it's a topological quantum computer or a conventional quantum computer, it would not have been, well, let's get one element to show the coherence properties. You have to go to very low temperature, you have to remove all of the excitations from the environment, all of the microwave radiation. In this case, you have to remove all of the quasi-particles. But you can probably do that. What probably you would have guessed would be the hard part would be to say, well, now you got to take 1 million of them and put them together on the same chip. And everyone would say, well, that's impossible. But oddly, we've already done that. The idea of integrating technology to the level not just of 1 million, but 1 billion working transistors on one chip, weirdly, is behind us now. So it is my belief that studying for a long time how to get 1 or 2 or 3 of these things to work, and knowing that we already know how to do this, means that I think that the next step after the creation of a handful of these states will be very fast. These things work at low temperature if they're doped correctly. There's nothing magic about this technology in going to the quantum regime. So I think that we should not imagine ourselves recapitulating Moore's law over the next 50 years, where we have to reinvent all of the miniaturization, step and repeat, mass production that produces millions or even billions of transistors on a chip, because we already did that. Now all we have to do is get a few of these guys working, and I think it'll be very fast to produce a working machine. That's a philosophy or a statement of faith, but I think that the real shock is that we've done that already, not that we've been able to make one non-abelian excitation. So I'm optimistic that these little gizmos will turn into a technology, in not that many years. Thanks. There's not time for questions.
One quick question. Thank you, John.
Yeah.
Thanks. It's really inspiring talk, Charlie.
Thanks.
Can you tell us about the poisoning? You said 20 milliseconds is a long time, which to me sounds like a very long time compared to a single operation time. However, if you are having 1 billion qubits in your chip, I mean, just a single one to fail could be, that would be very likely in a much shorter time. So my question is that, is there a way to implement quantum error correction to correct for those poisoning errors?
I think that that's a question at the forefront of
of theoretical study, I asked people who are expert at this recently what they consider to be the redundancy factor for correcting errors of topological character. And rather than the typical 10 to the 4 kind of numbers that you hear for conventional qubits or quantum error correction, I've heard numbers between, let's say, 10 and 100. And the reason why is because of these very long coherence times. That is, a lot of what this redundancy for quantum error correction does is repair coherence. It's not that it's fixing fabrication errors. It's that it's repairing coherence. So it's basically parity checking these objects, and when they flip, the faster they flip, the more you need. Because these are topologically protected, the redundancy is forgiven. In fact, you could even say that's the entire point of working with topology. It's obviously much further behind than superconducting qubits and other qubit technologies. Why bother? The answer is because if the coherence time is long, the redundancy needed for quantum error correction is correspondingly shrunk. And so if you can get a 10 to 100 redundancy between the logical error-corrected qubit and the physical qubit, that's the motivation for the topological approach.
One quick question. Perhaps Mikko, you can
Just about this magnetic field, how these modes are really crossing each other. I guess there are several other suggestions anyhow which could produce such a thing. Is this true, or?
You mean other things that can disguise themselves as that?
That's right, yeah. I mean, it's wonderful that there is some dependence that you can now sort of relate. Yeah.
I'm sorry. It wouldn't be Kondo. Okay, Kondo will split magnetic field, but it won't go like this. Right. So I don't know. In fact, you can imagine, right? As soon as we publish this, 18 papers are going to appear saying, here are 18 different things that could disguise themselves. And everyone's keeping their mouth shut now until we go out and publish the paper. But no one has mentioned them to me.
Yeah, so thanks a lot, Charlie. Let's thank the speaker again.